Yep. Okay. So I'm just going to go down the list of people that I see. Yeah, people with A's in their names are unlucky. So Alicia, do you want to share perhaps, do you have any ideas on any of the answers to the questions? No, Alicia? Okay, no, Alicia. Annabelle, do you want to try and answer any of the questions?
I got question 1. I thought you have to look in the graph.
Yeah.
On the left. And I thought the cladding must have a lower refractive index than the core. So we have to look at 900 nanometers or larger, nonetheless.
Okay. Does anybody have a more accurate? So that's the reasoning is correct. So the core index has to be larger than the cladding index. So that's very true. Did anybody figure out the exact wavelength?
I didn't know how to figure out the exact one, but just by reading carefully, I thought around 780.
Yeah, exactly. That's exactly right. All right. Thank you, Annabelle. B. Bosch. I'm not sure if that's a first name or last name.
Yeah, it's for both.
Okay.
So both with a B. Anyway, I didn't really know how to solve this one.
Okay. Okay. Does or perhaps instead of me going down the list, does anybody have an idea on how you would solve this this particular one? Okay. So if no one volunteers, then I have to go down the list. All right. Then next on the chopping block is BV Amstel.
Well, so the reason I didn't react just now is because I don't know.
All right. So no one has any idea. Go ahead. Just attempted solutions. Any idea on how you would calculate this? A beginning of a solution.
I thought we would need the width as well of the fiber.
You have the width of the fiber. It's 100 microns.
Oh, I didn't see. That would have helped.
All right. No one else? No one's gonna give it a shot? Okay. So the idea is that the ray or the light beam can travel along any angle, so any path that respects the condition that it's that is below the critical angle for total internal reflection, right? So there's a certain number. I mean, there's technically an infinite number of paths that it can take, but what we can consider are the two extremes. So which path in the waveguide, so if we have a waveguide that looks like this, which path is the shortest according to you?
One straight through the middle.
Exactly. And which one is the longest?
The one with the most fractions at the edges.
Exactly. So the most bounces, and the most bounces occur when you're right on the limit of the critical angle. So now if we take that into consideration, you can calculate using these equations the difference in optical path between the two, or the difference in group velocity or propagation time. Okay, so that's how you would do that. So given that there is a possible difference in the propagation time between those two extreme modes, can you think of any application where this might be a problem? The fact that there's potentially quite a big difference between the shortest one and the longest one. So I have the values right afterwards, but can anybody think of an application where this might be problematic? And a hint in the question is that there are some that you've seen in this class where it might become a problem.
It's still a bit unclear to me, the last question, because it says there, what's the duration of the longest duration of the pulse? Isn't it still going to be 10 picoseconds?
Nope.
I mean,
That's
and
exactly.
a delay
So,
between the moment that you
yeah.
need the pulse and the moment that you get the pulse. So there's going to be a delay. That I get, but isn't the duration still 10 picoseconds?
No, exactly not. So the point is that if you send, the question is, what is the longest and the shortest? So let's say you send a pulse that part of the pulse goes straight down the middle, and part of the pulse goes at a different angle, right? Let's say the most extreme angle. Like if part of the pulse goes straight down the middle, then that part is going to go along the quote unquote fastest line, and that will take a certain amount of time to get there, right? And then if part of the pulse, if different parts of the pulse go along all the different possible angles, they will all arrive at destination, but with a little bit of delay, right? And there's a little bit of delay that's different for every single angle that the pulse can, that the ray of light can travel. And therefore what happens is your pulse is spread because part of it arrives, the fastest possible time is straight down the middle, and part of it arrives with the slowest possible time, which is the light which bounces the most, and every other thing in between. And therefore what happens is if you do the calculation, let's see real quick. Yeah, if you do the calculation, you see that there's a full nanosecond difference between the shortest and the longest travel time. Okay, so then that means that if you send a 10 picosecond pulse, it can potentially spread until it's a 1 nanosecond pulse, which is 100 times its original duration, right? So one of the examples that you didn't see in this in this course is telecom. So we like in the internet industry now, some of us may have access to fiber optic internet connection. And the way that works is by sending bits of signal down optical fiber. So it's literally a laser that goes on or off that sends light through the optical fiber, and you have a decoder at the end that converts that back into binary signal and then analyzed by the computer. If you're sending, let's say, 10 pulses, and each one of those pulses is 10 picoseconds long and separated by 10 picoseconds, if you use this kind of waveguide, then what happens is that those pulses are going to spread out so much that you won't be able to tell the difference between them, and therefore you can't recover the information, the binary information that's being sent. Does that make sense to everybody? Okay, so again, I'm going to ask the question. So are there any applications in this class? Hint, you've had, I think, several classes on this particular subject where the fact that there's different optical path lengths could be a problem. So, which technique do you use that you studied in? Dirk, have they had this class already, or am I the one who's making a mistake? The optical path length measuring technique. Okay, Dirk's not there anymore. Okay. So are any of the techniques that you've studied so far, do they measure the optical path length of light? Does that ring a bell for anybody?
OCT?
Where you need,
Yes.
yeah, the
Interferometry.
yeah.
So any interferometry measurement, including OCT, is going to have a big problem with that, because OCT measures the delay between one beam and another, right? But now if you have inside a waveguide, if you're using this waveguide to transport your light, the light can take two different paths, or actually an infinity of different paths, each of which has a different path length. And therefore, it's going to completely jumble up your OCT signal, and it makes it completely unusable. Okay? So another application that could be super problematic if you have this kind of quote-unquote bad waveguide is if you're using, if you're trying to do laser therapy. So if you're trying to blast, let's say, a piece of cancer with a high-power laser where the pulse has to be very, very short so that it has very, very high power, so like a large amount of energy in a very short amount of time, that doesn't work anymore, because then if your pulses are completely spread out, you lose that peak power. Okay? All right. So this is a picture that describes kind of what happens in these fibers. So when you have different modes, if you have an initial pulse, what happens is that that's going to spread out along the different paths. So ignore for the time being the different peaks and look only at the envelope of the peaks. And that's essentially what's going to happen. So we're going to go from this peak right here to this much broader one later on. Okay? So this is what we call modal dispersion. So a mode is just a way that light can travel in the waveguide. Now, the other type of dispersion that I mentioned earlier is chromatic dispersion. And chromatic dispersion occurs because the index of refraction can change with the wavelength. And that's relevant because if you send a pulse of light that contains multiple wavelengths, not all the wavelengths will arrive at exactly the same time. So what happens is, typically, if you look at glasses, the index of refraction is lower at higher wavelengths. Meaning that the optical path is lower. I'm not going to say something wrong. Yes. Yeah. So it's lower at lower at higher wavelengths. Therefore, it will travel faster, and your certain colors will arrive before other ones. Okay, and this is going to result again in peak broadening. This time, even if you have a single mode, because the colors travel differently, your pulse will broaden as well. Okay. All right. So now, in the beginning, I mentioned. Well, before we go on. So far, is that like more or less clear? If you have a waveguide, the light can travel in different ways. These different ways result in different paths, different lengths, different times, and that's something that you need to account for depending on the application. It can have a significant influence. Okay, so far so good. Any questions? Okay. So a different type of waveguide is if we go back to the same 2D geometry here. So we have a waveguide that has a thickness of 2 rho, an outer cladding of a certain value. But now the the core index is no longer a single fixed value. It's a value that depends on the position in the core. This is something called graded index waveguides. And now, because of this, you have light is going to travel in a different way. Okay, so there's Fermat's principle in optics is one of the fundamental principles of optics, and it states that light will always travel along the shortest optical path. So we'll always try to minimize the optical path. You can derive Snell's law from this, and using this principle, you can figure out how the light is going to travel inside this graded index. So just to understand why this is relevant, so imagine imagine you have a waveguide where the index is maximum in the middle, and it goes down towards the edges linearly or whatever shape. If you send light down the middle, the light, if it goes in a straight line, it's going to be going along a shorter physical path, but along a higher index. Okay. Similarly, if you send light at an angle, it's going to be traveling a longer physical path, but through lower index. And so there's this kind of effect that compensates one another, where light naturally will travel along the path that combines these two effects. So the physical distance that the light is traveling and the optical, the index of refraction, in order to achieve the shortest optical path. Okay, so if you take Fermat's principle, you separate it into partial differential equations, do a little bit of math, change the form, you come to this one differential equation for this 2D case. And basically, when you solve this differential equation, you can calculate exactly along which path your rays are traveling. Okay? So one thing that's interesting to note, when you look at graded index optics, this is the full theoretical way of analyzing it, but there's a much more intuitive and simple way, in my opinion, to look at it. You have to imagine that you have your waveguide here, and if you subdivide it into really, really small little thin slices, if you take a differential approach, essentially, you can say that each slice has its own index of refraction. And then what you can do is you can just use Snell's law very simply to predict. You have your incidence angle and your exit angle, and you can predict how much the light is bending. Okay, so that essentially is like doing n1 sin theta 1 equals n2 sin theta 2, and so on and so forth. So here we have cosines, because instead of using the incidence angle, I'm using the angle with the optical axis. And what you see is that if you do it for the first slice, well, you have your index at position 0 and your angle at position 0. Now, Snell's law says that that's going to be equal to the index at position 1 times the angle at position 1. And that angle is equal to the index of position 2 times the angle at position 2, and so on and so forth. And so what you see is that no matter where the ray of light is, this value, so the index at that position multiplied by the angle at that position, is the constant. And that is the invariant in graded index optics. Okay? So what you can do, or actually before I keep going, so now, can anybody tell me how can you say under which condition the ray of light will be guided? So when can you guarantee that the ray of light will always stay inside your core? I'll let you think about it for just 1 minute. So a hint, the answer to that question is partially in the second question right afterwards. So how can you guarantee that the light will always stay inside the core, that it will never leave into the cladding?
As long as you're under the critical value, right?
Well, okay, but what is the critical value in this instance? Because what happens is, since you don't have a step index profile where you have a core index and a cladding index, you can no longer calculate the critical angle between the two, because what happens is as you get closer to the cladding, the index of refraction gets closer to that value. I guess a profile would have helped. Yeah, okay. Let's do quick paint. Best teaching tool ever. Boom. Boom. Okay. 1 second. Okay. And you all see my magnificent paint drawing. Okay. So let's say you have an index profile. So the point of the graded index is that it's no longer a step function like this. It's now some function that varies. So it could be a straight line, it could be a curved line, but there's a gradient in your index, which means that when you get to the boundary here, which is which is the edge, which we usually call rho, the index of refraction inside the core is basically the same as the one in the cladding. So how would you define the critical value at that moment? It's not a wrong answer. You're like, if you think of it mathematically, you can maybe look back at the definition that we had of the critical angle. Maybe you can still find the correct answer. Okay, so if we go back to the definition of the critical angle, right? Right here. The definition of the critical angle is when the angle of incidence becomes, so the angle between the normal to the surface and the interface, and the beam becomes 90 degrees. Right? So it's, in other words, it's also when the angle relative to the optical axis, so now the angle between the blue line and the z-axis becomes 0. It's when the refracted beam becomes parallel with the interface. Okay? So if we take that and we apply it here, it means that the light will be guided when you do, if you take this little analogy here, where you have n1 cos theta 1 equals n2 cos theta 2 equals n3 cos theta 3, when you get to the edge, the very edge of your waveguide, you will have ni, which is basically at the boundary you have ng cos theta something, but theta is now 0 because the ray of light has to be parallel, otherwise it will go through, right? So then if your theta here is 0, your cos becomes 1, and basically you would have ni cos theta I equals ng, right? But because of this chain of equalities, you can write the same thing where it's the initial index and the initial angle has to be equal to ng cos theta 0. And so basically you can define your critical angle like this. So long you respect this value of the invariant, or you can also calculate, you can isolate the theta c and find the critical angle, your light will be guided. Okay?
But I still have a question, because if the indexes are the same, as you said, the light has to be parallel to the edge, but how do you make sure that it is parallel at that point?
Well, so by solving, so if you take this this chain of equalities, and you go all the way slice by slice all the way to the edge, you will have n I, whatever value I is, cos theta I equals ng, which is because now you're reaching the cladding, times cos theta, and then the theta there is the angle of the beam that's in the cladding, right? But we saw that the condition for total internal reflection is when that theta value is now parallel to the optical axis, right? So if theta is if the ray that's being transmitted is parallel to the optical axis, theta equals 0. Therefore, cos theta equals 1. And then you end up with only, so imagine you had a cos theta right here, except that one goes to 1. And so you only have this condition.
Yeah, so the parallel is more of a result than a sort of initial.
Yeah.
That's where I was confused.
Yeah.
Okay.
So it has to be parallel at the cladding, and if it's parallel at the interface, then it will not exit after the interface. It will go back down. Yeah. Okay. So the second question, if you were trying to calculate at which height in the waveguide the beam turns around, how would you do that? It's a very, very similar question. So what we just determined now is how do we guarantee that the beam turns around at exactly the cladding? Okay, so it's exactly the same reasoning as previously. So if you take this chain again, you have a certain position in the chain where theta I becomes 0, and therefore you can calculate from that where depending on the initial angle, you can calculate at which index is it going to turn around. Okay. All right, so this is just an interesting result. So if you take this chain of equalities and you express it in differential form or just with infinitesimal small variations, and you use an expansion where you say that if you take a step forward in a function, it's the same as evaluating the function and then multiplying by that step times the derivative. You can solve all of this and get all the way back to the initial Fermat principle. So the initial differential equation which describes the ray path, which was derived from Fermat's principle, which is a much more complicated method. So using only this chain of equations, you can get back to the same results. Okay, so one of the most interesting, so right now we were discussing the general case where it's any index profile, like my fantastic drawings. It can be a curved line, it can be a straight line, it can be, well, wobbles aren't really useful, but it could be any wobble. Some of the really interesting profiles is the so-called parabolic profile. Now, in this specific shape, and using the approximations here, when you have a square root of 1 minus something very small, which is the case in this, you can approximate it as follows. If you plug this into the general equation, which we saw in this slide, if you plug it into this equation, what you end up with is, so if you do the math, you end up with this value right here. So the second derivative of x, and remember, x is, well, okay, here in the picture it's y, but the x-axis is the vertical axis, and the z-axis is the horizontal one. If you have the second derivative of x is equal to minus alpha squared times x itself, does anybody know what the solution to this this differential equation is? No? Okay, so it's a standard solution. It's basically a cosine and a sine. So if you take the second derivative, forget the factors in front, but if you take the second derivative of cos alpha z, it's minus alpha squared cos alpha z. So it's the minus alpha squared times the function itself. And the same is true for the sine function. And then these parameters here are extracted with the boundary conditions, the boundary and initial conditions. So what's interesting here is two things. The first is that if you have this particular parabolic profile, your rays of light are no longer straight lines. They're now sine. They're sine and cos waves. And so you have to understand that we're not talking here about, I'm not saying that light is a sine wave in terms of the variations of the electrical field. I'm talking that the path of the light is sinusoidal inside the, and it looks something like this. And so now, depending on, so if, assuming that the ray enters in the middle, depending on the angle, you're going to have a different amplitude, but it's always going to be a sinusoidal pattern, as you can see here. Now, what's very interesting about this particular path is that the parabolic index profile, if you do, so strange. So if you calculate the optical path through here, so the optical path, the length of any function. So if you take the line of a function, which is curved or whatever, the length of that line can be calculated with this integral, right? This corresponds to the physical path of the ray. It's exactly the physical distance that the ray has traveled. Now, if you want to calculate the optical path length, it's just the physical distance multiplied by the index of refraction. So then what you have to do is just do the integral of this physical distance multiplied by the local index of refraction. And what happens actually with this parabolic index profile, which I won't show because it's a long development, but it actually minimizes the difference. It minimizes the modal dispersion, which means that no matter which angle you come in, all the modes, so all the different possible ray paths, end up having the same optical, or very close to the same optical path length. So if you go to the extreme angles, it changes a little bit, but if you stay within reasonable, quote unquote, reasonable angles, they end up having all the exact same optical path. And so what that does is it means that this problem that we had with the other waveguide, the step index waveguide, no longer applies because we have, like the modes don't have dispersion. You still have chromatic dispersion or other effects, but modal dispersion is minimized with a parabolic index profile. So if you wanted to use pulsed light, it might be useful to use something like that. Okay?
Sorry, I got one question.
Yes.
They all have the same, how would you call it? The same pathway. Isn't it the same direction? Is the same direction?
As you can see in the figures here, each line corresponds to a different path. So they have different paths, but they have the same. They travel the same optical path length. Does that make sense, Vlad?
Yeah.
So the physical distance that they travel is different, but because the index of refraction, so that's my bad. That's something that I should draw for you guys. Okay. So the parabolic index profile looks, and now please excuse my horrendous drawing, but it's roughly a parabolic shape like this. So in the center of the waveguide, you have the core, what they call the core index, or the N0. And on the edges here, you have the cladding index. And in this particular one, what happens is, even though this outer blue line, for instance, travels a longer physical distance than the yellow or the purple one, because it's traveling in a lower index, the optical path length is smaller, and therefore the effects compensate each other, and they end up having very, very close optical path lengths. Is that okay? Does that answer your question, Vlad?
Yes, it does. Thank you.
All right, perfect. All right. So that was planar waveguides. That was just 2 examples. There's a bunch of other stuff. But the key takeaway here is that waveguides can only guide light when your core index is higher than the cladding index. Otherwise, there's no possibility of total internal reflection, and therefore the light will just be lost. Different index profiles will have different trajectories. So I showed the step index one, which is just like bouncing, or the gradient index with a parabolic, which turns out to be sinusoidal shapes. Other shapes exist as well. Different trajectories, different paths can have different path lengths and propagation speeds, which is what we call modal dispersion. And in these waveguides, depending on the type of index profile, you have something called the effective index or the invariant, and that can characterize your ray. So it tells you all the information you need to know about your ray in order to determine its shape and its other properties. The parabolic index profile minimizes modal dispersion. And then you have the other dispersion effect, which is chromatic dispersion. So those are some of the major effects and the fundamental things about guided optics. Okay, so the next part that we're going to talk about is we're going to go into fiber, and we're going to see the limits of what I just showed you. So this is geometrical optics. It's talking with rays of lights, and there's a point where that fails. Let's take a 10-minute break, and then we'll come back and talk about fibers and the next steps. Okay. All right. So see you guys at let's say 3:05. 8 minutes.